Hello, you're welcome back. Okay, so still on thermal expansion, we're going to be looking at some question and their problems. So I have one, okay, I want to start with. The question goes like this. A steel plug has a diameter of zero point 0.1 meter, okay? So the initial diameter D1, I've already atomized that is zero point 0.1 meter. At 30 degrees Celsius, that is the initial temperature, 30 degrees Celsius. Okay, so now the question is, at what temperature will it fit exactly into a hole of constant diameter 0.09997? So now the diameter, the final diameter, okay, that we are looking at is 0.09997. Okay, we are looking at the temperature at which this initial temperature will change. We're looking at the temperature at which this initial diameter, okay, we change to this final diameter D2, which of course is 0.09997 meter, okay, given that the linear expansivity of the steel is 1.1 times 10 to the power minus 5. So the question is find the final temperature theta 2. Of course, you know very well that for us to solve this, we apply the formula for the coefficient of linear expansivity, which we know is alpha is going to be equal to L2 minus L1, then divided by the initial let L1, then the temperature change theta 2 minus theta 1. Okay, so the whole idea is for us to find the final temperature. So now I have to make the final temperature the subject by cross multiplying first. I have to start cross multiplying. Right, if I cross multiply, I'm going to have alpha L1, then theta 2 minus theta 1 equal to L2 minus L1. That's the very first step. The second step is I'm going to divide both sides by alpha L1, okay, so that I'll be left with just the bracket theta 2 minus theta 1. So invariably, now if I do that, I'm going to have the theta 2 minus theta 1, okay, being equal to L2 minus L1, then divided by alpha L1. So finally, now my theta 2 now, which of course is the final temperature I'm looking for, is going to be equal to L2 minus L1 divided by alpha L1. Then minus theta 1 goes over, it becomes plus theta 1. So all I just need to do is to put my parameters into the expression. I will get my final temperature. Okay, so let's start putting our parameters. Okay, of course, you know that the final length given is 0.09997, while the original length is 0.1. Then divided by the alpha, which of course is giving us 1.1 times 10 raised to the power of minus 5. Then multiply by the original length, which of course is 0.1. Then plus theta 1, the initial temperature is 30 degrees Celsius. So I have to put that here, 30. So now let's actually flow with this. Theta 2 is now going to be equal to. So my calculator will do my work, will do the work now. I'm going to have 0.09997, then minus 0.1. So here I'm having minus 0.0000000. Okay, or better still, I put it in a standard form. Let me put it in a standard form. So um, how many zero do are we looking at there? I have one, two, three, four, 4 0, and of course, if I put that in standard form, that's going to be minus 3 times 10 raised to the power of minus 5. Okay, so divided by 1.1 times 0.1 will give me 0.11, all right? Then, of course, times 10 raised to the power of minus 5, then plus 30. Of course, 10 raised to the power of minus 5, we cancel 10 raised to the power of minus 5, so I'm now left with minus minus 3 divided by 0.11. So let's do that. Minus 3, okay? Minus 3 divided by 0.11. So I have minus 27 approximately. Minus 27 then plus 30. So let's subdo that. Plus 30. So invariably the final temperature that I need is 2.7, approximately 2.7 degrees Celsius. Okay, so as simple as that. As simple as that. So I'm gonna be looking at another question also. Okay, let me clean up. Okay, so you can still go through it one more time. You will get to understand it better. All right, so this is another question. I will read the question and then I write the parameters. The question goes this way: the ends of a steel rod of cross-section area. So the steel rod have a cross-section area of 4 centimeters square. Okay. Then of course you know very well that I have to convert the centimeter square to meter square. Okay, first of all, if I want to convert that, I have to convert the cm first to meter. To convert cm to meter, I have to divide by 100. So if I convert 4 cm to meter, I have 0.04 because I divide by 100. Then of course I have to square it because I want to convert to meter square. So I'll end up having 0.0004 meter square. Okay, so that is the area that I have there. So let me continue reading. Okay, so area of 4 centimeters square are held rigidly between two fixed points at a temperature of 30 degrees Celsius. So the initial temperature, okay, theta 1 is 30 degrees Celsius. 30 degrees Celsius. I'll write that down. All right. Now the question is determine the force. So this time around we are looking for the the force, okay? The force of compression. So determine the force which opposes the expansion when the temperature increases. Theta 2. That opposes the expansion when I increase the temperature from 30 degrees Celsius to 120 degrees Celsius. All right. Now, given that the linear expansivity of the steel is 1.2 times 10 raised to the power of minus 5 per Kelvin, comma, and your modulus of the steel is 2 times 10, okay, raised to power 11 Newton per meter square. So, of course, you know very well what you are looking for. Okay, we are looking for the force, the compressive force, or the compressive force is the force that actually that prevent expansion. Remember, okay, expansion is increase in length. So, if I want to actually prevent expansion or to compress that increase in length, I'm gonna actually use a compressive force, okay, in form of stress. Okay, now let's actually evaluate that. Remember the formula. The formula for that force is giving us your modulus E multiplied by the area multiplied by the linear expansivity, then multiplied by the change in temperature. Don't forget the formula for that, the force of compression. Okay. All right. So now from the question, we already know that the your modulus is giving us 2 times 10 raised to the power of 11. The area we've already calculated gave us, okay, let me put that in standard form. If I put this in standard form, that's going to be 4 times 10 raised to the power of minus 4. Then multiply by uh, the alpha, linear expansivity, 1 times 10 raised to the power of minus 5. Then temperature change, theta 2 minus theta 1, that's going to be 120 minus 30. Okay, so let's do justice to this. Okay, so I'm going to multiply this, the numbers. Then I treat the powers of 10 separately. So first I'll start with 120 minus 30. Of course, 120 minus 30 is that's going to give me 90. So what I'm going to do is I multiply 90 by 1.2, then times 4, then times 2. So that gives me 864. Then I work with the powers of 10, okay? The powers of 10, which of course, applying distance, you know what's going to be. That's going to be 11 minus 4, 10 raised by 11 minus 4, minus 5. Those are the laws of indices, okay? I'll write the base and add the powers. Why? Because call that law addition law. Okay, so because I'm having 10 raised power 11 times 10 raised power minus 4 times 10 raised power minus 5. So all I just need to do is just to write the base, which is 10, then I add up the powers. 10, 11 minus 4 minus 5. So now let's proceed. I'm going to have 864, 11 minus 4, then minus 5. What do I have? That's 2. So that's going to be times 10 raised to the power of 2. Okay, so which invariably, of course, this is 100. So 100 multiplied by 864, that's going to give 86400. And that is measured in Newton because it's a force. So I hope that is well understood. Okay, so please take note of this, and we are going to continue with the other type of expansion, which of course is area expansion and volume expansion. Okay, so I will do that in the next video. All right, see you in the next video. Thank you very much.